Hi guys, it's been a long time. Uh, today we will learn about exciting and Inrush current on transformer, why it happened. But we didn't learn about transformer yet. But it's works. In the future we will learn about transformer. So now we need to know about it. This Inrush current and exciting current. It's also related reactor. That's why I explained. So first of all, I wanna say is here. There's a transient state and a steady state. You know, so in the transient state, Inrush current happened, and then steady state, exciting current happened. But there's just big differences between them. I explain. Okay, what happened? So first of all, we need to learn, memorize RL circuit. So as you guys remember, here's switching R, L. This is RL circuit, right? So when I switch on off, the current is what happened. Yes, as you guys should know, it's an asymmetric, current waveform happened, right? Because of RL's property. And what I want to say is, okay. So okay. This is transformer. I will. This is load. So this is here, primary part, and this is the secondary part. But I said at the no load situation, exciting current and inrush current happened. Inrush current happened. At no load situation is it's opened here, so there's nothing here. So at this time it happened, exciting current and inrush current. But I said inrush current in the transient state it happened, and then exciting current in the steady state situation it happened. But as you guys know, latent current, I will say IM. For example, IM is 100 ampere. Exciting current is just 30 to 5% of I current. Latent current is percentage. But inrush current, 8 times to 12 times between times, current's magnitude happened. That's a big problem, even though this is not fault current, but it happened, because of whenever we, switch on and off, because L's property. So if it happened, what happened was, we have a current, circuit breaker. But circuit breaker's main purpose is, to protect our power system, right? Or equipment. But actually, this is not fault current, but it's open the circuit. But we don't want to open the circuit, that's a makes problem, right? Or as you guys know, the negative, magnetic forces happened, but it's proportional to the current to 2. The power, negative power was. That's why, yeah, we need to reduce inrush current. So to understand inrush current, we need to first know about here. saturation. I already made a lecture about this. You guys have to watch it, okay? First of all, this is a iron core, right? Iron core, the transformers. So what I set at no load situation. So secondary part is opened. So this is primary part. So what I wanna say is, okay, this is a totally RL circuit. You know, this is just transformers RLs. Mostly X is almost the circuit. You know what I mean? X is really big. But as you guys here's a saturation curve. It could be a pH cover. Here's H or here's B. It's the same results, but you guys can see here the slope. Slope means L is I pi, but we need to pay attention here. Look at that. The saturation part, L's slope is gonna be more flat, like no angle, almost zero, which means if L is zero, reactance is X is zero. So look at that. I equal Ohm's law if we're using Vx, right? Because this is X is really big, So almost X, the resistor. But what I mean is, since we're using a voltage system, this is a constant value. But what happened? Suddenly, X is a little bit, sharply reduced. We cannot explain with Ohm's law, you know. Yeah, actually, we could explain, but what I mean is, what we need to know it, why it happens today. How it could be the R is, X is sharply reduced to almost zero. So that's why the current is really big. Why it happened? So that's why I explained we need to know about saturation. One part is, so we need to remember is at the saturation part, the XL is almost zero, right? So that's why X is almost zero. That's why I is really, the magnitude is really big. So let's see here. What I want to say is here, the exciting current is here. But here's, you guys can see, yeah, it's better to remove this. Here's exciting current is here. And this is symmetrical right now. But look at that. But this is I pi. So L is I pi, right? I pi. So I will say this is a saturation part. Okay. So what I wanna say is this, okay, and this green line is a saturation part. Also here is exciting current is also here. So we use it. Exciting current is this line is a saturation part, from here. But actually, we use it till almost this point, The limitation of the current is we use this red line. So we almost get to here. But because of as you guys know, RL circuit we use, right? But whenever we switch on and off, asymmetrical happened. You can see here, I said before here, DC opposite happened, right? And that's why, yeah, like this, have this asymmetrical, waveforms happened. But what I meant is here, I said this green line is a saturation point. But it actually almost, almost we use it to here, the current is line is. But because of the asymmetrical waveform happened, this point happened. That's why it's a oversaturation part. You know what I mean? Oversaturation part. That's why, the current is, x is almost zero, almost. That's why the current is really getting bigger. This is, inrush current, why it happened. Actually, inrush current happened the first time, and then exciting current, at the state, as I showed you guys before the situation happened. You know what I mean? So that's why we need to learn about this situation. So what I mean is the important thing is RL circuit. Whenever we switch it on and off, asymmetrical waveforms happened. But in the transformer, because of that, the inrush current happened. You know what I mean? So as you guys also can remember, if the voltage is degree is as you know guys, in the RL circuit, I is lagging, right? 90 degrees, right? For example, yeah. This is V. I is from here. Oh, God, this color is red color. I is 90 degrees. This is 90. So I is 90 degrees lagging, right? In the RL circuit. But what I mean is when the V is 90 degree, there's no inertia at the I, right? That's why if each situation happened, there's no asymmetrical waveforms not happened. But what I mean is since we use a three-page system, it cannot be, symmetrical, asymmetrical happened because we use, three-page system. So, and the two more bigger, the inrush current, look at that here. Let's move on. So here, you guys can see here, latentability point B here. When this is a hysteresis, we already learned, right? And because of the, even though we removed the current, there's, retentative, flux is still, exists in the core. That's why it makes more bigger the inrush current. Okay, this is optional. But what I meant is that the important thing is the RL circuit, because of the series system, we cannot avoid the asymmetrical waveforms. But actually, there's solutions. I will tell about a little bit about solutions. But what I mean is, since we didn't understand this part, how we work at the industrial part, So if we know about this concept, we could make a solution. Or what we could suggest something. Like look at that. Here's one example is in rush current, it's include mostly second harmonics waveforms. So we use also second harmonic filters, one of the ways. Or we also use another way is using auxiliary reactors to reduce the L's property. Actually, this solution is no need to learn about right now. Just I explained, if we know about this concept, we could, suggest some solutions to find out how we figure it out this. Yeah, today is kind of difficult, right? If you didn't know about the saturation part and the Earth's property, you cannot understand. So that's why we accumulate our knowledges. Yeah, that's it today's lecture. Thanks, guys.